So let's review what we've covered in Unit 6. Unit 6 is about the Lorentz Transformation. And that's a way of taking the spacetime coordinates for an event as measured in one reference frame and converting them to the spacetime coordinates in another reference frame. We started, as we often do, by thinking about space and not space-time. So we looked at a two-observer diagram in a coordinate system. So here this is space, x and y, not x and t, and would have x and y axes, and then another coordinate system that's simply rotated. And so if we wanted to read things off of this rotated coordinate system, we would calibrate it by following a circle from the y-axis, for example. So this has a distance of 4. Distance from the origin is 4. On the y prime axis, what's a distance 4 from the origin? That would be here. And the geometry and algebra behind this is the recognition that a circle is the set of all points that's a constant distance from the origin. And so the markings, the calibrations are connected via circles. And the formula for a circle is this. So then we took that idea and applied it to space-time, and we worked through with a good bit of detail how that would look. So in a two-observer coordinate system, we said, all right, well, the t-axis, that would be a clock at the origin of the prime system, the moving system, that's moving to the right. And so the t prime axis is just the world line of that clock. How would we calibrate it? Well, we'll say, okay, in this reference frame, in the primed reference frame, when the moving observer says, hey, it's 4 seconds now, that would be a space-time interval in that reference frame, and thus it must be that space-time interval in all reference frames, because the space-time interval is frame independent. And so we said, all right, well here, in the unprimed frame, here's a space-time interval of 4. And then we said, you know what connects points of constant space-time interval, space-time intervals? Well, it's a hyperbola, not a circle, but a hyperbola. The metric equation, which is basically this, gives a different geometry. So we have to think about hyperbolas instead of circles. And so the markings, the calibrations on axes are connected by hyperbolas, not by circles. And so we argued that this will have a slope of 1 over beta, because it's just the world line of the center clock in the moving frame. And then we said, well, what does the x prime axis even mean? Well, that would be the set of all space-time events that's simultaneous at t equals 0. And using that argument, along with a radar method construction, we realized that, you know, we might have been expecting the x prime axis down here, but it's not. It has to be up here. And it has a slope of beta. This angle and that angle are equal. Okay, so a little more quantitatively, we took these this calibration idea, did a little bit of math on it, and said, all right, here's how we would calibrate a t prime axis. There's this quantity gamma, 1 over 1 minus beta squared square root. Comes up all the time in relativity. It's sometimes called the Lorentz factor or just a gamma factor. And then this is how we would calibrate that. So delta t is gamma delta t prime. So gamma is always greater than 1. And so if a delta t prime, let's do t, 1, 2, 3, 4. So like here's a delta t prime that's 4. What would, right there, what would that look like in the unprimed frame, the at-rest frame? Well, I would go over here and read that off. It's a little bigger than 4. And that's the algebra that would go along with that. We calibrate x prime axis, this axis, in exactly the same way. We read primed coordinates via parallel lines. So here's a point in space-time. In the at-rest unprimed frame, it has an x of 4 and a t of 5. We just read it off the graph. In order to read these axes, we follow not a perpendicular, but parallel. So here I go parallel to the t prime axis, and I say, all right, well, where does this hit? And I said this is roughly 1.6. Maybe it's more like 1.7. If I wanted to get the t prime reading, I don't go perpendicular to the t prime axis. I go parallel to the x prime. So the lines between these two lines are parallel. So I go there, and I say, all right, well, where is this point? 1, 2, 3, I don't know, around 3.8. So that's how we read events, space-time coordinates, off of a two-observer diagram. So we can see all at once the different coordinates, t and x, t prime and x prime, that the two different observers will have for the same point in space-time. So then we said, all right, well, this is a nice geometric construction. Let's think about that algebraically. Let's come up with a formula so we don't have to necessarily, draw these lines and then go, maybe it's 1.6. So we did that, again, a bit of math, and I ended up with the Lorentz transformation. So here it is. This is doing one way. This is if you know the primed and you want to figure out unprimed. This is if you know the unprimed and you want to figure out the primed. And those parentheses should not be floating up in the air like that. Okay. So again, this is the Lorentz transformation. It's the relativistic version of the Galilean transformations. It's a dictionary. It lets you translate events, the space-time coordinates for an event, in one reference frame into another reference frame. From the primed frame into the unprimed frame, or the unprimed frame into the primed frame. So it's a bilingual dictionary. So let me end with just a few comments. First, just a reminder that we've gotten here, Lorentz transformations, which in some ways, I don't want to say it's the climax of the course, but it's a pretty significant accomplishment. We've corrected the Galilean transformations. A lot of relativity is captured in just these equations. And we got there only with the assumption that the speed of light is the speed of light, that it's constant in all frames. So we took that assumption as our base, and so that version of the principle of relativity, and then done algebra and geometry, and we're landed here. The other thing I want to say is that the Lorentz transformation, here's a bunch of algebra, and the two-observer coordinate system, here's a picture, are different complementary ways of representing the same relationship. And this is a pretty common thing in physics. Often one develops a geometrical picture and an algebraic picture. And I would say resist a temptation to say, oh, I'm a graphical person, I'm just going to do graphics, or I don't like graphics, I'm just going to do symbols. I think one of the things that physics is good, and people who do physics and get good at it, they learn, is to be able to go back and forth between these two, so that you can push through some calculations with algebra and you can start to see the algebra because you have this picture. And you might have this picture and you can start to see algebra appear off of that. So again, these two things are closely related. Okay, so those are the Lorentz transformations. So this brings us to the end of Unit 6. We've derived the Lorentz transformations, we've constructed two-observer space-time diagrams, and we've seen how to use them. We'll continue with this line of reasoning in Unit 7. The topic there is a phenomenon known as Lorentz contraction. We've seen that the time coordinates between two events is different for different observers. And we're going to see a similar phenomena for spatial coordinates. In particular, we'll see that the length of an object is not constant, that the length of an object is different in different reference frames. So that's what we'll get into in Unit 7. See you then.